Dear students, dear colleagues, let me introduce myself. My name is Mária Kaňuchová and I am a teacher of chemistry at Technical University of Košice. I'm so glad you invited me for this event, and today I would like to tell you something about relatively new, very nice and sophisticated method for surface analysis, X-ray photoelectron spectroscopy. Some of you maybe know this method like electron spectroscopy for chemical analysis. I am a teacher of chemistry at Faculty of Mining, Ecology, Process Control and Geotechnologies. I work at Institute of Earth Resources. This institute focuses on scientific research, educational and expertise activities, covering wide range of processes which include obtaining, processing, utilization and protection of earth resources. The emphasis is particularly on processing and obtaining of solid, liquid and gaseous raw materials, geotechnology, ecotechnologies and waste management. Because I am a chemist, the main subject of my scientific research is preparation and characterization of new environmental materials, waste materials or raw materials by this XPS method. Why is it nice to have this device for the surface analysis? There are several benefits, but firstly is in one measurement we are able to measure all elements of periodic table. Secondly, this method is non-destructive. Thirdly, the relative concentrations of elements can be determined from the photoelectron intensities, and very important advantage of XPS method is its ability to obtain information on chemical states from the variations in binding energies or chemical shifts of the photoelectron lines. It means that sometimes it's very good, it's nice to know the oxidation state of the elements. For example, antimony in the oxidation state 3+ is more toxic than antimony and in oxidation state 5+. And this method is very clever. It's so nice for measuring these characteristics. X-ray photoelectron spectroscopy is a surface analysis. Surface analysis is a part of analytical chemistry which study the part of a solid that is in contact with a gas or vacuum. When two phases of matter are in contact, they form an interface. The term surface is usually reserved for the interface between a solid and a gas or between a solid and vacuum. The surface is considered to be that part of the solid that interacts with its environment. Surface and structural materials analysis can drive understanding of the microstructural characterization of materials. And this is very nice information about the materials which we study. And this method is relatively new. I thought that this method is relatively new. X-ray photoelectron spectroscopy was developed in the middle of the 1960 years by Kai Sieben at Uppsala University in Sweden. In 1981, Kai Sieben was awarded a Nobel Prize for Physics for his work with XPS. The advent of commercial manufacturing of XPS equipment in the early 1970s years enabled the placement of equipment in laboratories throughout the world. And 10 years ago, our university bought this XPS device from Germany company Specs by the help of European funds. And we are on this slide, you can see the equipment at our university. I like to show this device our students or our visitors because the look is specially and unusual, and we are so happy that we were able to buy this equipment. The basic parts you can see on in this picture. The basic parts of this device are power supply, hemispherical analyzer, and X-ray source. The principle of this method is that the surface of the sample is irradiated by photons from X-ray source. Electrons from the surface of the sample are emitted in the hemispherical analyzer, and there these electrons are collected by their kinetic energy. Then we have got the electron spectrum. You can see the spectrum in this picture, and this spectrum represents the dependence of emitted electrons from the surface on their binding energy. In this picture, you can see the survey spectrum of pure copper, and later I will show you our measurements and our experiments. The relationships between kinetic and binding energy you can see in this picture. Kinetic energy equals energy of photons minus binding energy and minus work function. Work function is typical part of every or each devices which are manufactured and which is manufactured. Okay. In this picture you can see the hemispherical analyzer. The energy analyzer works as an energy filter in which the electrons move in a radial electrostatic field between two concentric spherical electrodes, with only the electrons with the desired energy passing through the system. The analyzer is supplemented with an input optics that provides electron braking or accelerating and allows for an appropriate choice of voltages to select the area and the spatial angle from which the analyzer accepts the incoming electrons. In the practice, the basic parts of the XPS device you can see in this picture. Our device has lamp with the two anodes, magnesium and aluminium. These anodes have the different energy. Then there are necessary are the pumps. The pumps are very important because they keep the ultra-high vacuum in the ambient of the device. Then we have power supply. Power supply is, with this power supply we are able to set the conditions for measurements, the current, the value of voltage, and with the power supply we are able to check the pressure in the ambient, and you can see that the pressure in the device has a value 979 up 10 minus millibars, and the conditions in the device, all measurements providing under the ultra high vacuum. Device has two chambers, antechamber and main chamber. In the main chamber, there is necessary to have ultra-high vacuum permanently, and the antechamber is necessary because with this chamber we are able to put the sample into the device and to keep the ultra-high vacuum in the main chamber. In the main chamber we are able to put 3 samples for measurement, and the 4th sample is sample of silver. This silver is permanently in the chamber because we use it for the calibration of the device. Now, I would like to tell you something about our measurements, something about our investigation. We prepared several very interesting new and environmental materials and characterized it by the XPS method. Because we are the faculty of ecology, and because we are the faculty of ecology, we tried to prepare and to characterize some problematic waste materials. It is plastic materials, and we tried to select it and characterize by XPS method. The motivation for this study was the increasing need of recycling waste plastics in the cleanest separated form. Relatively inexpensive methods of physico-chemical separation of plastics is based on the different wettability of their surfaces. Because most used polymers are relatively highly hydrophobic, which would lead to their collective flotation in water, the study was aimed for the selective suppression of the hydrophobic character, hydrophilization of one of the most common plastics, which is polyethylene terephthalate. XPS method gave interesting information about the actual mechanism of the chemical reactions at the polyethylene terephthalate surface, which was changed by the alkaline hydrolysis. By comparing energy spectra, we found that the hydrolysis by water with increasing temperature decreases the percentage of the carbon-oxygen bond, which is characteristic of an ester group, and at the same time increasing the percentage of binding of carbon-hydrogen bonds. These changes indicate a disruption of the structure of the polyethylene terephthalate. At the alkaline hydrolysis by treatment with sodium hydroxide, was observed the disappearance of the double bond carbon-oxygen, which is associated with the binding of sodium from sodium hydroxide solution to the oxygen from ester group. The cleavage of the polymer chain into smaller oligomers indicate the percentage drop in a single bond, carbon-oxygen and carbon-carbon. In this picture you can see that on the surface of the sample we see the element sodium, which was incorporated into the surface of the polyethylene terephthalate. The obtained results showed that increasing the temperature and the concentration of solution sodium hydroxide has a marked effect on the hydrolysis of the polyethylene terephthalate surface and leads to cleavage of the polymer chain into smaller oligomers or monomers. Wettability of polyethylene terephthalate foils evaluated by XPS method measurements is enhanced after their pretreatment in sodium hydroxide solutions at concentrations up to 8% and temperatures up to 60 degrees Celsius. Therefore, both the sodium hydroxide concentration and temperature are important factors of pretreatment, stimulating together the hydrolytical attack and consequently the hydrophilization of polyethylene terephthalate foils. These significant changes on the surface of polyethylene terephthalate material enable the separation of polyethylene terephthalate and polyvinyl chloride plastics by flotation. And this is very interesting information for recycling plastic materials. Slovakia largely obtains electricity energy from power plants, and that means the formation of fly ash. Preparation of geopolymers means the use of fly ash in practice, and we try to use the waste materials from the fly ash to the creation of geopolymers. Geopolymers are inorganic synthetic ceramic materials that form long-range covalently bonded non-crystalline networks. Commercially produced geopolymers may be used for fire and heat-resistant coatings and adhesives, medicinal applications, high-temperature ceramics, new binders for fire-resistant fiber composites, toxic and radioactive waste encapsulation, and new cements for concrete. In this study, we tried to create geopolymers from 4 types of fly ash samples from Slovakia, derived from various combustion processes, and we investigated the chemical bond and the changes in the chemical bond during the mechanical activation, and then we investigated the formation of new aluminium oxygen silica chemical bonds by the XPS method, and the changes in these bonds during the milling. In this slide, you can see the electron spectra of these 4 samples. These lines, the red lines, are the spectra before the milling, and the yellow spectra are after the milling. From the obtained spectra of the 4 samples, we can see changes in the peak positions of silica and aluminium atoms, which indicate the dissolution of the elements in alkaline solution. Significant decline size of the peak of aluminium atoms indicates a beginning of oligomer condensates and creation of a 3-dimensional aluminosilicate structure. Formation of intermediate silanol silica hydroxide group and production of basic siloxo group. Solidification of the 4 samples indicates a significant decrease of oxygen. Peak positions of atoms of carbon, oxygen, silica, and aluminium confirm condensation of orthosialate molecules via reactive groups of silica and silica-oxygen-aluminium hydroxide. This formation and creating cyclo-trisialate structure and the formation of the polysialate chain. The creation of the polysialate chain you can see in this picture. This is very interesting because the creation of this chain is very important in the creation of geopolymers. Mechanical activation of fly ash by intensive grinding was utilized as a step in the development of flexural and compressive strength of geopolymers. The results of geopolymerization experiments clearly indicate that the particle size, morphology, and reactivity of fly ashes influence the final properties of geopolymers. The structure of fly ash has an impact on the flexural and compressive strength of geopolymers. The changes in the structure of prepared geopolymers were investigated by XPS method, and we confirmed the changes by this method. In this study is very nice and very interesting. Was very interesting for me because in this study we investigated the leaching of antimony from the drinking bottles, and it was very interesting for me. By the healthy, you will see in this picture. You can see that by the XPS method we confirmed presence of antimony in the surface of the drinking bottles. We bought the drinking bottles prepared from the polyethylene terephthalate, and we bought two types of these bottles. One of them was blue colored, and one of them was clear bottle. And we studied the leaching of antimony from this bottle after the different conditions. The leaching of antimony from the drinking bottles, you can see in this slide. In this slide, we confirmed that the leaching of antimony from clear plastic from blue plastic is more rapid than leaching antimony from the clear plastic, and the leaching of antimony by carbonated water is more rapid than the leaching of antimony by the tap water. Very interesting is information. If the plastic bottles are on the sun, the sunlight rapid the leaching of antimony from the plastic bottles. And after this study, I realized that the using of polyethylene terephthalate plastic bottles like drinking bottles are a bit danger for my health, and I stopped to use these bottles. In this spectra, we confirmed that after the leaching of the antimony by the water or by the sunlight, the structure of the polyethylene terephthalate is changed because the spectra of the carbon are changed, and it confirmed the degradation of the polyethylene terephthalate structure. Very interesting is the decrease of amount of carbon from polyethylene terephthalate plastic. The value is changes, and it means that the basic structure of polyethylene terephthalate loses carbon-oxygen bonds, and as a consequence of this, the polyethylene terephthalate structure degrades. How I said, after this study, I stopped the using of polyethylene terephthalate bottles, and I tried to drink tap water or to drink the tap water. Very nice was study of superconductor by XPS method. At our institute, we prepared the lithium-ion arsenic superconductor with the cooperation of Slovak Academy of Science. Superconductor is conductor without resistance or without energy losses. This material is very interesting and it's very nice, and we characterized this material by XPS device. By this device we confirmed the presence of iron, arsenic, at the surface, and we confirmed the oxidation state of these elements, because the oxidation states of these elements is very important in the structure and in the behavior of this sample. By the XPS method, we confirmed a presence of iron in oxidation state 3+, and we confirmed the presence of arsenic anions with the oxidation state 3-, and we confirmed that this superconductor is conductor with the N-type conductivity. And the measurements at the Academy of Science, at the Slovak Academy of Science, confirmed the superconductor's behavior of this material, and it was a very nice work with the cooperation of Slovak Academy of Science. This superconductor works at low temperatures, and in USA they try to prepare long conductors from this material. To use and because the fly ash is a big problem as a waste material in Slovakia, we tried to use the fly ash for preparation ultramarine blue pigments. Natural ultramarine blue pigments have been of broad use in the past and present in their natural form, lapis lazuli. They belong to the group of mineral pigments characterized by the sodalite structure and colored sulfur species, chromophores, encapsulate inside. Nowadays, there is an urgent need for their cheaper analogues synthesized from other minerals, or if possible from waste materials. We tried to prepare these ultramarine blue pigments from fly ash at our department, at our university, and the main aim of this work was to elucidate a possible connection of these original parameters, sulfur-based chromophores, with a final color of the ultramarine blue pigments: green, blue, pink, violet, red, and greenish blue. This is the structure of the base structure of the ultramarine blue pigment. Into the cage, sodalite cage, the chromophores are encapsulated into the cages, and by the XPS method, in this picture you can see the results of the measurements. We prepared four samples, and we prepared two samples with very nice blue color, and by XPS method we confirmed that in these colors, in these samples, we confirmed yellow and blue chromophores. These chromophores are very important for the creation of this color. The other two samples One of them was red and one of them was gray colored. And in the red sample we confirmed the red chromophores, and in the gray sample we confirmed only the blue chromophores. There wasn't the yellow chromophores, and the finally color of the sample is gray. In this work, it has been found that the ratio of the blue and yellow chromophores, rather than their amount, together with the amount of sodium cations with respect to that of aluminium and sulfur atoms, represented by the sodium-aluminium-sulfur ratio, is crucial for the preparation of a nice ultramarine blue pigment from fly ash. We were very happy that the preparation of ultramarine blue pigment was successful, because the conditions of preparing are very demanding, but this preparation was useful at our university. The another using of fly ashes was the formation of geopolymers from fly ash and from the metakaolin. We tried to investigate the differences between fly ash and between the metakaolin. And the aim of this work was to develop methods for working properties prediction of geopolymer materials based on the starting materials. In this slide you can see the electron spectra of prepared geopolymers. By this spectra we confirmed the bonds between silica and hydroxide, between silica and oxide and silica, and between silica oxide and sodium. These bonds confirm the creation of the silica aluminium and silica sodium chain in the geopolymers, and the samples were analyzed for a period of 28 days. During this time, changes in peak positions of atoms of oxygen, carbon, sodium and aluminium were observed. Changes in peak positions of silica and aluminium atoms clearly demonstrate the dissolution of silica and aluminium in alkaline solution. Aluminium and silica atoms released during activation from alkaline oxides are indispensable building blocks in the polymer structure. The greater purity of metakaolin suggests sharper peaks in the XPS spectra. This investigation proved that metakaolin is better than fly ash in geopolymers, but kaolin needs more energy to convert it to the metakaolin, whilst fly ash is a waste and doesn't need any energy. So fly ash is more cost effective than metakaolin. Thus fly ash may be recommended for preparation of the geopolymers. It will save energy required for calcination, and at the same time it will eliminate the waste and pollution. This investigation, which I thought about, their investigation were realized at our university, at our department, and because we cooperate with the Slovak Academy of Science, and it's a very nice cooperation with this institute. We studied the mechanochemical reduction of ilmenite concentrate by addition of aluminium, and it was very nice work because in this work we were able to study the changes in the oxidation state and the changes in the structure of ilmenite. In this picture you can see the very nice changes in the atom, in the iron atom, the changes in this oxidation state. Iron after the milling changed was changed from the oxidation state 3+ to the oxidation state 2+ after the milling, and the XPS survey spectra have demonstrated changes that are caused by a mechanochemical reduction in the surface stoichiometry of the products. The detailed spectral lines of titanium and the iron confirm the creation of the amorphous rutyl phase according to thermodynamic predictions. These measurements and this investigation, I think that these measurements are very important for the and to get some information about the materials and about the structure, and these informations are very important because then we know what we have to do later, and what we prepared. Okay, by this method we are able to characterize what we prepared and if the structure is okay. Now I have some questions for students because I explained the principle of the XPS method. I would like to ask the students if it is possible to measure liquid or gas materials by this method. Thank you very much.